Hello. Today we're going to talk about photosynthesis and we're going to focus on the light-independent reactions. But just as a quick overview, we're looking at a chloroplast, and if you recall, during the light-dependent reactions, light and water enter the thylakoid and then oxygen comes out the other side. And the purpose of the light-dependent reactions is to make energy that's going to power step number 2. It's energy in the form of ATP and NADPH. So what we're going to talk about today is how carbon dioxide enters the stroma, and then it uses ATP and NADPH to be able to produce glucose, the sugar. So the ultimate goal of both stages of photosynthesis is to be able to produce the sugar glucose. So last time we were inside of a thylakoid. Today we're going to be outside of a thylakoid in the stroma. All right. So light-independent reactions. That means this part does not need light. Now, it couldn't happen if it didn't have the products from the first stage, so it kind of needs light, but it doesn't directly need it in this phase. And I like to split it into 3 steps. The first step is called carbon fixation. In biology, when we use the word fix, we mean like mix or incorporate. So we're going to incorporate a carbon during this phase. So we have to start with a molecule we've never heard of called RuBP, and it has 5 carbons. So 1, 2, 3, 4, 5. Let's add all of our carbons there. And then it also has 1 phosphate on each end. So that's a phosphate. Like, remember how ATP has 3 phosphates? These are phosphates like that. So this is a compound called RuBP. And RuBP is going to combine with our input for the light-independent reactions. What goes into the light-independent reactions? Carbon dioxide. So that's 1 carbon oxygen, 1 carbon atom and 2 oxygen atoms for carbon dioxide. So we're going to combine RuBP and carbon dioxide using an enzyme called Rubisco. That is an abbreviation for a longer name that does end in ACE, just so you know. And then when you combine RuBP, which has 5 carbons, and carbon dioxide, which has 1 carbons, you get a 6-carbon molecule. 1, 2, 3, 4, 5, 6. And it still has the 2 phosphates on the end of it. Phosphate, phosphate. This molecule doesn't even get a name because it's really unstable, and it like instantly splits into 2 3-carbon molecules. So if you split it in half, each molecule would have 3 carbons. And then don't forget the phosphates. And these little 3-carbon molecules are called 3-PGA. We don't need to know what it stands for. We can just use the acronym, or you can call them 3-carbon molecules. And let's go ahead and track our carbon. So here we have Rubisco combining with carbon dioxide. I'm highlighting that carbon. And let's just say that it incorporates like in the middle right there, so then it would be right there. So we can see that one of our PGA molecules has the carbon from the carbon dioxide, and the other one has all the carbon from the RuBP. So important thing that happened in this stage was RuBP combining with carbon dioxide to form PGA, 2 molecules of PGA. And the carbon fixation part was us combining carbon with RuBP. Sometimes my board erases when I draw a circle around it. Those are good times. All right, the next step is called reduction. So to start with, let's redraw the same thing that we had before on the previous slide, which was 2 molecules of PGA. So 3 carbons, 1, 2, 3, 1, 2, 3. And they each had a phosphate on them. And let's label them just because labeling is nice. 3 PGA, 3 PGA. And remember that one of these carbons was highlighted because it came from our carbon dioxide. I can't remember which one we highlighted before, but it's okay, it doesn't really matter. So in this step, we are going to add in our products from the light-dependent reactions. So we're going to add in ATP, excuse me. This is like the adenosine ribose group. And then there's 3 phosphates that are connected to ATP. 1, 2, 3. And then we're going to add our other product, which is NADPH. And that holds the electrons. Okay, so the next thing that's going to happen is we're going to use the energy from the ATP and the NADPH to be able to rearrange our PGA molecules. Even though I didn't draw it, you can picture like there's all of these O's and H's coming off of these molecules. We just typically don't draw them because then it would make the structure look really messy. But what happens when they rearrange is all of those O's and H's get shifted around. So to us, the molecule ends up looking the same way based on how we draw it. But again, if we could see the larger structure, we can see that it actually has been rearranged. And this rearranged molecule is called G3P. So we get 2 molecules of G3P, and of course our carbon atom is still there. And then what else would come out of this stage is our low energy forms. So now instead of ATP, we have ADP with 2 phosphates. And then we have our low energy form of our electron carrier, NADP+, with no electrons in it. And this ADP and the NADP plus are going back to step 1 of photosynthesis, the light-dependent reactions, so that they can get remade into their high-power forms so that this cycle can keep happening. So, big picture, we used energy to turn PGA into G3P. And congratulations, you're almost halfway done. So if you can just stick with it for a few more minutes, we'll be in good shape. The last phase is called regeneration. So can we start by redrawing what we had before, our G3P molecules with 3 carbons. And the phosphate on the ends. And I'm highlighting that 1 carbon that came from our original carbon dioxide. So this is exciting. These G3P molecules, one of them is actually going to leave the cycle, and it is going to get turned into glucose eventually. So as the cycle continues, G3P molecules have to leave so they can get made into glucose. C6H12O6. And all carbohydrates have this like ring structure. And yes, we know it also has the O's and H's, but I'm not drawing it because believe it or not, I'm actually trying not to confuse you guys. But the point that I want to make here is that the carbon dioxide from the atmosphere ends up in glucose. I did not mean to highlight that a different color. There we go. How many G3P molecules would have to leave to be able to make one molecule of glucose? 6, because only one of them is actually leaving. And then you might be wondering, like, why? What are the other ones doing? They need to get recycled. If it's a cycle, that means it has to be able to happen over and over and over and over again. So the other G3Ps are going to be recycled back into that RUBP so that the cycle is able to continue. And then, what do you think is going to happen with the RUBP? It's going to combine with a carbon dioxide molecule, and it's going to form a 6-carbon compound that then will split into 3 PGA. And if you haven't noticed yet, I just resaid carbon fixation. So literally, we're going to use our final product here to be able to like start the process over again and again and again, and it will just keep happening. Thanks for listening. I know this is confusing. Please email me all your questions.